Hello, friends. So I am back with another mineral group, that is the amphiboles, in the series that we are continuing for the detailed mineralogy for the GSI or other such examinations. So we have already done olivine, pyroxene. Now let us look at the amphiboles. So the amphiboles, they are the double chain inosilicates. Unlike the pyroxenes, which were the single chain inosilicates, the amphiboles, they are the double chain inosilicates. And they are a very important mineral of the uh, igneous and metamorphic rocks. So the amphiboles, they occur in a wide range of environment as a common constituent of both igneous and metamorphic rocks. So we'll see in the later slides how they occur, and especially in the paragenesis part. So once we look at the igneous rocks, the uh, hornblends, or sorry, the amphiboles, they occur in from ultra basic to acidic and alkaline types, and they are particularly common in the intermediate members of the calc-alkaline series. So I hope you understand all these terms. Then they form an important mineral of the plutonic rocks. Okay. Also, they occur in large varieties of regionally metamorphosed rocks which have formed under the condition of green schist to lower granulite facies. That is, we find them in the rocks that have formed at a temperature of 300 degrees Celsius 2 kilobar to 900 degrees Celsius 9 kilobars. You can understand their importance by the fact that they can be found in low grade as well as high grade metamorphic rocks. They occur less commonly in the environment of contact metamorphism, but they are not uncommon, and they can be found in contact metamorphosed limestones, dolomites, and other calcium rich sediments. So, if you look at again this Bowen's reaction series, you can see that they are the third in the line to be formed after olivine pyroxene of the discontinuous series of crystallization. And you can understand that the temperature of formation of amphiboles is definitely lower than that of olivine and pyroxene. So, as I had told in the beginning, they are double chain inosilicates. So, their general composition is SiAl4O11, means that the Si to O ratio will be 4 is to 11. Now, this is a picture. So, here we have the double chains. If you remember, in pyroxenes, there were the single chains as the repeating units, while in amphibole we have the double chains as the repeating units. So it would look somewhat like this. Yeah, that way. Okay, then you can keep on repeating these units to form the actual mineral structure. Yeah, this way. And the double chains, they repeat along their lengths at the interval of 5.3 angstroms. So this defines the C parameter or the C axis of the unit cell. Now the unit cells, they are separated and bonded together by strips of M cations. I'll just show in a bit what are M cations, which specifically are Mg and Fe. And apart from it, there are some additional OH ions also. Now, why these OH ions, they exist in the amphibole structure? So if you look at these chains over here, you can find that the ring which is forming over here, it allows the space for a hydroxyl ion to sit in. That is why the amphiboles, they can allow the inclusion of OH minus ions inside it. Okay, but if it was a single chain structure, this space was not there. That is why the OH could not come and fix in the lattice structure uh, of the pyroxenes and amphiboles. M cations here, they lie in the strips of linked MO6 tetrahedra. Okay, the oxygens of which plus OH minus form the apices of chain forming tetrahedra. So if you try to understand this line. What does it say? That M cations, they lie in the strips of linked M or O6 tetrahedra, and the oxygens of which uh, they along with the OH minus, they form the apex of the chain forming tetrahedra. So if we look at the diagram, see this diagram over here. Oh, so if you look at this, you can see that this is the tetrahedra 1, tetrahedra 2, tetrahedra 3, and tetrahedra 4. All these four tetrahedra, they form the repeating units. Okay, so see this here, we have four of these as repeat, so double chain. So we have these double chain, and there, once you look at the uh, the cations which are linking the apex over here, it has some cations, while once the bases of the tetrahedra they are aligned, we have some more cation or the void spaces over there. So if we look at this diagram here, we can see that these M cations, they are linked at the apex. Okay, so this will be M1, M2, M2, and M1. Okay, but if we kind of look at the fixation of an OH minus ion, then we can have one more, and that will be here. Here. So we will have M3 as well. So we have M1, M2, M3, and then M1. While at the bases, we have M4, A, again M4. So this is how the cations are attached. Very clear it is that once the apex, see the apices of the tetrahedra, they are pointing towards each other, definitely due to the lack of space, the cation site will be smaller. While if we have the base of the tetrahedra being aligned, we will have the larger space and the cation sites will be larger. So one thing we can understand over here, that the cations sitting in M1, M2, M3 will definitely be of a smaller size than those of at M4 and A. So if we look at this structure, then here you can understand that you have to how to draw this structure. Draw four triangles. Just let me add a screen over here, like a screen, and then I'll show you how to draw it. Very easy to draw. One, two, three, four, and then again like this. One, two, 3, and 4. So you drew two chains of four tetrahedra. After that, you have to remember that the smaller cations on the top of the apex here and here, and the larger ones here. 1, 2, and 3. So this is how you can make these chains go on. So you can repeat these alternatively like this. 1, 2, 3, 4, this way, and then draw the larger ones over here and then smaller ones over here. Okay, so once you draw it this way, you will be getting the entire chain coming up. Okay, like this way. So you will have smaller ones over here again, and the larger ones here. So you can see now that we have got a structure like this. So what about the cleavage pattern now? Remember that the cleavage patterns run along the bases. So it will be running this way, this way, this way, like this. So you can see here that the cleavage is running at an angle. Okay, and this angle I will just show you. So that was how you can make this structure. Now, if we have to look at the uh, angles over here, so this red line, this denotes the cleavage. Cleavage. We all know that hornblende has two sets of cleavage which are aligned at an angle. And what is that angle? See, this angle is 126 degrees, while this angle is 54 degrees. This is the reason why the cleavages in the hornblende, they are, or why I'm saying hornblende again, this amphiboles, they are arranged at an angle of 126 and 54 degrees. That is just because of the arrangement of these linked chains, double chains, along with the sides. So if we come to the detailed structure, so this is what I was saying, that they show two sets of cleavage patterns at an angle of 54 and 126 degrees. Now, let us come to this detailed structure. So in this structure, I will just first explain this part to you, and then we can go ahead. So if you look at this, we have these tetrahedra, four tetrahedra which are linked together, which is T1, T2, T3, and T4. And this is the OH ion. Okay. Now we have this in place. So if you look at this structure, what are these ones? These is M2, M1, M3, M1, M2. This is that side. The linking of these sides, the size of cations M1, M2, M3, M4 determine the way they are surrounded by oxygens of the tetrahedral chain. So how they'll be surrounded? Now, look at the basal part. So as I had mentioned in the beginning, that these are not the individuals, but they are the strips. This is a strip of M cations. This is one strip. So this is another strip. See, so we have two different strips. M1's M1, M2, and M3 being smaller in size, they are placed at the apex of the tetrahedra. See, while the M4, A, and again M4, they are larger and they are placed at the bases of the tetrahedra. So, how to draw this? Very simple. Again, first draw the tetrahedra. This is the bridging oxygen. Again, bridging oxygen, bridging oxygen. So we have got four tetrahedra. Again, just reverse the pattern this way. Now that we have got the tetrahedral chain, we have to now draw the cations, which are at the apex will be this way. I have drawn four. So this will start with M2, M1, M1, and M2. What about the M3? M3 will come once you place the OH minus. OH is here. Okay. Similarly over here, this is OH, the blue color. And so now we can place our sites M2, M1, M3, M1, M2. And the larger ones, time and again I am mentioning, the larger ones which are here. So this will be M4. M4 draw A in between these two, and then M4 over here. Okay. Now I hope this you understood how to draw it. Then just beside it, just beside this arrangement, now you have another repeating unit, the central part which you can see over here. So this one, now what we need to do, we can draw the same pattern on this side. I'll draw it a bit smaller so that we can arrange it. So, but this will be inverted. Bridging oxygen, inverted this way. And then the upright one. Okay. Now we can see that the where is the apex line? It is here. So we have M2, M1, M1, M2, and then let us now draw the OH minus, which is here and here. So we will get the M3 now. This is M3. Okay. Now let us see how they are all linked together. And for linking, I am drawing that by purple line. First of all, draw straight lines from the M sides to the oxygens like this way. This way. And then join the oxygens of the apex of the tetrahedra so that the strips can be made this way. Okay, this way, like this. Now you can see that we are getting the actual shape. So now what will happen? Let us join this and this. Then join this and this and this and this. After that, join this way, this way, this way, this way, this way, and this way. So now we have linked the M1 with the apical oxygens, and then you have to link the M4. How it is going to get linked? So first of all, M4 gets linked with this two oxygens. Then this oxygen is going to link with the M1 or M2, and then this way and this way. So you can see how this repeating unit can be seen in this part of the diagram. It's very easy. It looks complex because it is lot to draw, but it is very easy. So I am sure you understood that the smaller M1, M2, M1, I'll just use a pointer, M2, M1, M3, M2, M1 and M2. So M2, M1, M3, M1, M2. Okay. They are being linked to the alternating oxygens as well as OH minus of the apical part of the tetrahedral chain. Then you link M4 with these two, M2 with these two oxygens. Similarly here. Okay. So if you look at this part of the diagram, the later part here, so we have M2, M1, M3, M1, M2, M4. This is tetrahedra 2, tetrahedra 1, tetrahedra 1 and tetrahedra 2, and we have OH minus. So here you can see that the apical M sites, how they are linked, and the basal M4 and A sites, how they are linked to form these strips. So what you are seeing, this is the strip, this shape. This is the strip of the cations with M4, M4. This is oxygen 1, oxygen 2, OH minus, oxygen 3, oxygen 4, oxygen 1, oxygen 2, OH minus, oxygen 3, oxygen 4. Then we have these sites, we have M2, M1, M3, M1, M2, and then we are simply linking them together like this. And then the corner M2s will be linked with the, corner M2s, they will be linking with the oxygens of the second one. So it will be this way, like this. You can see here that this is now the strip of cations. So I'm sure you will be able to draw this diagram. This is a very simple diagram. Only you have to remember the position of the cations and the tetrahedra. So if you look at this, then which is this projection? This is the projection of amphibole structure, projection along the z-axis. And if you are able to draw this in the exam, once this question is asked, I guarantee you the full marks. You will be definitely awarded the full marks. So the amphibole structure shows two sets of cleavage patterns at an angle of 54 and 126 degrees. The size of cations, they uh, uh, they determine the way they are surrounded by oxygens of SiOLO4, AlO4 chains, and then in most cases the stacking of chains is to produce a monoclinic cell. Example is tremolite. Okay, so here you can see the formula for tremolite is Ca2Mg5Si8O22OH2. Remember, you will never confuse with the formula. If you can remember these, that Mg will be attached to M1, M2, M3 sites, while Ca will be attached to M4. So if we draw that strip over here again, M4, oh, sorry, like this, then so M4 is Ca. So we add here Ca and Ca. We get 2 Ca. Then M1 has Mg, M2 has Mg, M3 has Mg, again M1 has Mg, and then M2 has Mg. So how many we have? We got now Ca2 Mg5, and then of course we have the tetrahedra. So this was 1, 2, 3, 4 OH, 1, 2, 3. So this will be I should write T2 T1 OH, T1 T2, T2 T1 OH, T1 T2. So if we have uh, four tetrahedron each side, so that makes silicon as 8. And since it is the linking one, let me just show you over here. So in this case, this one oxygen over here, half over here, this is a bridging one over here, one over here, and then bridging one. And then we have this one as bridging one, half, one here, and here's half one. So we have 1, 2, 3, 4, Si4, and then oxygens. So let us see, half, half 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, half, that is 11. So O11. Multiply this by 2 because we have these two units. So it becomes Si8O22. So let us now go back to our formula over here that we were making. So T2, T1, T1, T2, they are making since they are twice in number, so we have 8 silicon, and then we will have 22 oxygens, and then see, we had one OH over here and one OH over here, so we have OH. Now this is the formula of tremolite. See how easy it becomes once you remember the structure. Okay. Now, once the M4 site, it is capable of containing other ions as well. So when M4 consists predominantly of MgFe, then larger calcium sodium cations, then mode of stacking can result in monoclinic. For example, it is coming to night, which is Fe2 plus Mg7 Si8O22H2, or an orthorhombic cell which is anthophyllite. Again the formula remains same, so these are the polymorphs. So remember, anthophyllite, Lite, sorry, antho phy double Lite, anthophyllite. So we have coming to night as the monoclinic amphibole, and anthophyllite as the orthorhombic amphibole, both having the similar chemical composition. So presence of similar but not identical sites in the amphibole structure, which will be M1, M2, M3 octahedra, T1, T2 tetrahedra, gives scope for the ordering of cations among them. So aluminum, it prefers A1 tetrahedra and M2 octahedra, while if we have ferric ion, it prefers M2 octahedra. All these studies have been previously done. Okay, let us now come to the chemistry. So general amphibole formula is A0 to 1 B2 C5 T8 O22 OHF2. Now here you have to remember that A is the A site. So again, if you wish to keep it in your mind, then let me draw the strip for you, the cation strip. M4 A M4. Oh, I'm so sorry, not here. Let's erase it. A will be here. So this will be M4 A M4. This will be M4, and this will be M1, or sorry, M2 M1 M3 M1 M2. Now A site, which is this, B is M4. Okay, so A0 to 1, A may have some cation, may not have some cation. B will be 2, that is the M4 will be having 2. C5, so C is M1, M2, M3. You can count 1, 2, 3, 4, and 5. And then T is the tetrahedra. So we have 8 of those, and then of course it will be silicon or aluminum tetrahedra, followed by 22 oxygen and OHF2. So four broad division of amphiboles have been done on the basis of predominant cations in the B site, which is the M4 site. So what is that? We can have calcic amphiboles, we can have alkali amphiboles, sodic calcic amphiboles, iron magnesium manganese amphiboles. So let us look at them. If we have orthorhombic anthophyllite or coming to night, then it does not have a cation in the A site, but the M4 site has 2 Mg. M1, M2, and M3 sites, they have also Mg, so there will be 5 Mg, and then tetrahedra is silicon tetrahedra, so the chemical formula becomes Mg7Si8O22OH2, wherein 2 Mg are located in the M4 and 5 Mg are located in the M1, M2, and M3. But if we have a monoclinic coming to night, then we have iron in the M4 sites, Fe2, and then of course the other structure remains the same. So we have the formula as Fe2Mg5Si8O22OH2. Then we come to tremolite. So tremolite, now it has calcium in the M4. Okay, calcium in the M4. So two M4 sites, we have two calciums, and then other formula remains the same as previous one. Now if we come to hornblende, and the interesting thing adds over here, that now we have either potassium or sodium ions in the A site, then two calciums in the M4. In the M1 and M2 we have magnesium, but M3 we have aluminum. and then tetrahedra is of silicon aluminum tetrahedra. So the general formula of hornblende now changes to KNa021, that is sodium or potassium, Ca2Mg4Al SiAl8O22OH2. So the tremolite and horn blend, they both are calcic amphiboles. The next, which is the alkali amphibole, that is example is glaucophane. So here we don't have any cation in the A site. M4 has two sodium ions. Now Mg3, so M2, both 2M2 and the M3, they have magnesium, and probably M1, two M1s, they have aluminum, and then it is a silicon tetrahedra. Now the formula becomes Na2Mg3 Al2Si8O22OH2. Simply by remembering the position of the M sites and A site, you can never get the formula wrong. And then sodic calcic amphiboles. So if we get the sodic calcic amphiboles, example is vinchite. A side does not have any cation, B has sodium and calcium, and then C, that is the M1, M2, M3, they have 4 magnesium, 1 aluminum, Si8. Now all these, they we have just discussed about the cation distribution in Mg end members, Ng end members of amphiboles. So here you can see that A site is equipped to hold the Na and uh, potassium. The B site, which is the M4, so I'll write here for you. M4, it can hold sodium, calcium, magnesium, ferrous, manganese, and lithium. The M1, M2, M3, M1, M2, M3, they can hold magnesium, ferrous, aluminum, ferric, manganese, zinc, chromium, titanium, and lithium, while the tetrahedra is of silicon and aluminum. Okay, so if you look at hornblende, the general formula of hornblende is NaK, as I just previously mentioned, that the NaK over here, it will be the A, this will be M4, all this over here, it can be M1, M2, M3, and this constitutes of the tetrahedra. So A, B, C, T. So here the hornblende general formula is this, but if we talk about the sensu stricto hornblende, it is Ca2MgFe4 Si7Al O22. Sorry, I just made a small mistake over here. This Al will be here. Just let me correct this formula. Sorry for that glitch. Ca2 MgFe4 Al Si7 Si7 Al O22 OH2. This is the correct formula. Okay, so this is how it can be written down. That is a sensu stricto hornblende. It crystallizes in monoclinic system, and this word uh, hornblende is used for the, I'll add AL over here. Sorry for that typing error. So term hornblende is used for the end member Ca2MgFe4Al, Si7AlO22H2, and amphiboles near it in composition. So it can be used for all calcic amphiboles with significant aluminum content. So this is how the chemistry can be dealt with. So if you look at the physical properties of the amphiboles, they normally have the hexagonal habit and occurring in black to green or dark green color. Streak is normally gray to white, luster is vitreous to dull. Importantly, you have to remember that they have these cleavages at 54 and 126 degrees. Fracture is uneven and they have a hardness 5 to 6. Now, important part while we are dealing with this is the paragenesis. The mineral description is not complete unless and until you talk about the paragenesis. So if you look at the extremely wide range of chemical substitutions possible in hornblende, so they include the substitutions may include those of MgFe, sodium, calcium, silicon, aluminum, Fe3 plus, Fe2 plus, oxygen, OH, and fluoride. So this leads to, so this wide range of substitution, it is a reason for the existence of the hornblende in a wide variety of rocks which include igneous and metamorphic petrogenetic conditions. Okay, so this is one of the important things. Thus, although hornblends are particularly characteristic of intermediate plutonic rocks, they can also occur by primary crystallization in basic and ultra basic rocks, as well as in rocks of acid and alkali composition. Okay, so we can have hornblende occurring in intermediate plutonic rocks. They can occur in basic rocks. They can occur in ultra basic rocks. They can also occur in the acidic and alkaline composition rocks as well. Okay, so this is it. So primary hornblende, it normally occurs in the rock of alkali basalt and calc alkali series. So primary hornblende, it occurs in the rocks of alkali basalt and calc alkaline series. Sometimes in andesites, hornblende, it is commonly accompanied with olivine. Okay, keep that in mind. So once we talk about the Mg to Mg Fe ratios, here the gabbros are characterized by more Mg rich hornblendes. Okay, gabbro, more Mg rich hornblende, more Mg rich hornblends. How much? So here Mg is to Mg plus Fe ratio, it will be approximately 0.75. While if we have Nepheline cyanide, or we have granites, here in both these cases, more Fe rich hornblende. So here the Mg to Mg plus Fe formula will be close to 0.5. Okay, so this is the variation. Now, hornblendes of basaltic and andesitic rocks, they normally are rich in alkalis and ferric ion, and they contain less fluorine. Okay, so this was about the igneous rocks. So now once we are talking about the metamorphic rocks, so hornblende is one of the most common constituents of regionally metamorphosed rocks. Hornblende is a common constituent of regionally metamorphosed basic or ultra basic rocks. Basic or ultra basic rocks, and it is stable under a wide range of pressure and temperature conditions. Wide pressure temperature condition range, and therefore hornblende can occur from the upper green schist facies to The lower part of granulite facies, so we can write it like this: upper green schist facies via epidote amphibolite facies to lower granulite facies. So you can see the range of hornblende, and why this is possible only because of the excessive wide range of substitutions it can make. Hornblende and plagioclase feldspar are the main and sometimes the only constituent of hornblende schists, hornblende gneisses, and amphibolites. Okay, so in the amphibolite facies, you can find the hornblende and plagioclase feldspar as the sole constituent. So let me just draw for you a diagram over here. I'll just take a minute. Okay. So if we look at this ACF diagram, I hope you all are aware that A is Al2O3, C is CaO, and F is FeO plus MgO. So if we look at this, this is the plagioclase, we have the diopside, then we have the hornblende, and then here it is garnet. Okay, so if we just simply draw it this way. So what is this? This is the ACF diagram that explains that in the amphibolite facies of rocks which have hornblende schist, hornblende gneisses, and amphibolites, here you will be finding hornblende along with the plagioclase feldspar as the sole or main constituent. Okay, the transition from green schist to amphibolite facies, which we just saw previously, so from green schist to amphibolite facies, it can be represented by the reaction, the transition from green schist to amphibolite facies. It can be represented by the reaction albite plus chlorite plus epidote plus actinolite. Okay, and then it will give us hornblende plus plagioclase. Okay, temperature approximately 55 degrees Celsius, pressure approximately 2 kilo. So this is how the variation occurs. At the higher grades of metamorphism, once we come to the granulite facies, in case of the granulite facies, the hornblende, it gets transformed to pyroxene uh, by a dehydration reaction. You can understand why, because we saw that being a double chain structure, it can hold OH. So once we remove that OH, what it will be? It will be hornblende plus quartz. It will give rise to OPX plus augite plus plagioclase and plus water. So this is the reaction that can uh, uh, change hornblende to change hornblende to pyroxene. Pyroxene in many igneous rocks also is secondary in nature and derived from primary pyroxenes. Some secondary amphiboles they are tremolites or coming to night, and but they have been given a common name, urelite. Okay, so if you get a question, what is urelite? Uralite. So it is a secondary amphibole. Secondary amphibole. And then this is applied to mineral with a habit of pyroxene and structure of amphiboles. It's a very important thing. It is the habit of pyroxene while structure of amphiboles. And what is this process called as? So the alteration of pyroxene to fibrous amphiboles, it is called as uralitization. Uralitization. What is it? It is the alteration of pyroxene to fibrous amphiboles. So this completes amphiboles, and here you have to take care of two things. First one is the structure, how to draw it, and then the location of the M sites. If you remember that clearly, you will never be doing the chemical composition wrong. And while writing such answers in the written examinations, I am sure you are getting going to get good marks. So I hope this will help you. See you in the next class.